Hello, Junior Lab Rats. This is your Lesson 19, Mechanical Waves and Sound. You probably noticed when you went to your class participation assignment and saw this video link that there were several other YouTube videos also posted there. You're going to want to have those ready to go because there are several points in this video where I'm going to ask you to pause and watch one of those videos. Those are the videos that I would typically play within the slideshow during class. So if it's easier for you to go ahead and open them all in separate tabs, that may be the quickest way for you to get to them. So let's get started. Sound waves. Now when I come to one of the boxes that we need to uncover to find your answer, I'm just going to pause for a beat and then I'll go ahead and clear it. Sound waves carry energy through medium, the most common of which is air. Each molecule will vibrate as a sound wave passes through. Sound is a disturbance that travels through a medium as a longitudinal wave. Sound waves push through air, causing areas of rarefaction and compression. And this little wave right here, this sound wave, will probably look very familiar to you because you did create a longitudinal wave with your Slinkies in Lab 18. Your vocal cords vibrate like a string from a guitar, harp, or piano. This vibrating is caused by the air you force through your larynx or voice box. There are tiny joints, muscles, and connective tissues that control how loosely or tightly you hold your vocal cords as you force air past them. The tighter they are held, the higher the pitch they produce. More loosely held cords, or cords that are longer in general, like those in men, produce a lower pitch. As both a vocalist and a scientist, I could go on about the physics of vocalization all day long. It's actually quite fascinating. You've probably noticed that men or teenage boys that have gone through puberty have a visible, we call it an Adam's apple. That is because their larynx has grown and their vocal cords are therefore longer, which is why voices are deeper. And at the end of this lesson, I have some enrichment on music and how music and physics work together. It is possible for humans to travel faster than the speed of sound. In 1947, Chuck Yeager of the U.S. Air Force was the first person to break the sound barrier or travel faster than sound. When an object travels faster than the speed of sound, it is said to be supersonic, and it produces a sonic boom, a loud bang. He did so by flying his plane at an altitude of 12,000 meters, where the speed of sound is slower, and traveling at 294 meters per second. In 1997, Andy Green drove his jet-powered car to a speed of 339 meters per second, breaking the sound barrier on the ground. Those people who have broken the sound barrier on the ground typically do it out in like the salt flats or places where you have a big, wide open, very flat, very smooth surface. Because I'm sure you've realized that when you're driving a car, you want to slow down when you go over a speed bump. So I guess you can imagine how even a tiny bump would feel when you're going super fast. Properties of sound. Sound waves are longitudinal waves. Many behaviors of sound can be explained using a few properties: speed, intensity, loudness, and pitch. Speed. The speed of sound depends on the elasticity, density, and temperature of a medium. Mediums with a high degree of elasticity, or the ability of a substance to bounce back after being disturbed, allow for sound waves to travel more quickly. Solids are more elastic than liquids or gases and are the best transmitters of sound. Sound travels more quickly in less dense substances and in substances with higher temperatures. In air of about 20 degrees Celsius, sound travels at about 342 meters per second. You're going to want to watch video number 1 now, the speed of sound in different substances. And please note that rather than elasticity, the narrator uses the term stiffness, but the same point is being made. Intensity is the rate at which a wave's energy flows through a given area. Decibel is the unit for intensity, and it's 1/10 of a bell, named for Alexander Graham Bell, based on the unit of power in the Bell system, which deals with telephony, or how telephones function. This is one of those units where we pretty much never use bell. We always use decibel. even if we're saying something is 10 decibels and it's really just a bell, we still say decibel. Our next little box here. Loudness is the physical response to intensity of sound, modified by physical factors. So here's a decibel scale for you, just to give you an idea. Breathing is about 10 decibels, which would be a bell, but we never say that. We just don't. And then loud things like fireworks or jets going by are up in the 130, 140 decibel range. Frequency and pitch. Pitch is the frequency of sound as you perceive it. Ultrasound is used in a variety of applications, including sonar and ultrasonic imaging. Sonar is a technique for determining the distance of an object in water, a type of acoustic location. Those below our typical hearing range are called infrasound. Now, you may remember, or maybe not, that in the electromagnetic spectrum, those below what we can see, red being our lower frequency, we call those infrared. Okay, so you've probably heard infra before in that respect. Sometimes you'll just hear it abbreviated as IR, and often you may come in contact with it with certain remote control devices use infrared. Also, there are animals that use ultrasound or something similar, like echolocation, which is common in dolphins and in bats. Resonance. All objects vibrate naturally, having a natural vibration frequency. If a sound wave exactly matches the natural frequency of an object, resonance occurs. If a sound wave or other vibration meets the resonant frequency of an object, the object may begin to vibrate very hard. If you've ever pushed a child on a swing, you recognize there's a sweet spot on the backswing at which your added force will have the greatest effect and the child can go higher and higher. That experience is similar to the concept of resonance. Now, you're about to watch a video, it'll be in this next slide, on the Tacoma Narrows Bridge. And what happened in this situation is the winds that were blowing happened to match the natural frequency of this brand new bridge. And obviously from the title, you can tell what happened to it. So go watch that video and come right back. Interference occurs when two or more waves overlap. We have two types of interference. The first is constructive interference, and this occurs when two or more waves combine to produce a wave with a larger displacement. We also have destructive interference, and this occurs when two or more waves combine to produce a wave with a smaller displacement. You can think about this, I think I've talked about it with you guys before, if you've ever played with one of those parachutes when you were a kid, like where everybody stands around the parachute and you bounce balls around on it. Your constructive interference is when everybody is going up and down at the same time, and suddenly you get a really big, a lot of height out of it when you go up, and it all goes down together, and it's kind of like amplified. Because everybody is doing the same thing. So the waves are matching up and producing a greater wave. When you get destructive interference, it's like what happens when they throw the balls on the parachute and everybody just kind of madly shakes it. Doppler effect. Doppler effect is a change in sound frequency caused by motion of a sound source, motion of the listener, or both. As a source of sound approaches, the observer hears a higher frequency. When the sound source moves away, the observer hears a lower frequency. This is why, if you are standing next to the street and a fire truck goes by, you can hear the pitch of the siren start as lower, then it'll be at its highest when it's right next to you, and then it gets lower again as you move away. The Doppler effect is used in medical Dopplers, such as the one our little rat here is modeling, and it uses the concept of ultrasound combined with the Doppler effect. So it's telling you how far away whatever is being imaged is with relation to the sensor. So you can tell depth and things of that nature. And it also is present with light, which is how we get redshift, blue shift, which we talked about at the beginning of the year, Hubble's law, and this is how we know that the universe is expanding. Combining sound waves. Now, this is a word that some of you are probably going to automatically pronounce wrong. This is called timbre, the quality of sound described by its timbre. The blending of fundamental tone and the overtones make up a characteristic sound quality of timbre, or a particular sound. If you closed your eyes and asked a violinist, a pianist, or a trumpeter or a clarinetist to play A natural, let's take A4, which is A440, that's the note that orchestras tune to, on their respective instruments, you'll be able to tell one instrument from another by its timbre, despite the pitch being identical. You could try the same experiment with singers and get the same results. Music. Most musical instruments vary pitch by changing the frequency of standing waves. Resonance is the response of a standing wave to another wave of the same frequency. We talked about resonance before, and this is what gives you the timbre of different instruments and voices. So now you're going to watch video 3, which is Professor Dave explaining standing waves and harmonics. Music. If what you hear has a pleasing timbre and clear pitch, it is considered music. Music is a set of tones combined in ways that are pleasing to the ear. It is important to note that not all cultures define pleasing in the same way, and much of what makes music recognizable and sometimes predictable is culturally influenced. Musical instruments are grouped into families, including strings, brass, woodwinds, and percussion. Arguably, keyboards may be another family, but also can be considered a combination of string and percussion, or wind, brass, and percussion. String and percussion is when you're talking about pianos, because there is a hammer and it strikes, which is percussion, the string, which vibrates, so you get string and percussion. The wind or brass and percussion is a little fuzzy. We're talking about pipe organs here. In that case, it's less of, there's not really like a hammer that strikes. What you get is a bellows that is moved, but it's the key that's pressed. So there's kind of a percussion there, but then a series of levers will move a bellows and will move multiple other smaller levers to force air through a series of pipes. And the pipes are both wind and brass on large pipe organs. So you have some that are called reeds, and they are smaller, usually wooden pipes, and then there are metal pipes as well. And the length of the pipe will control the pitch. Next box. Noise is a word used to describe a combination of sound waves that does not have pleasing sound altogether. Noise has no pleasing timbre or no identifiable pitch. Again, there are cultural influences at work here. Tones that seem to have no musical relationship are considered dissonant. Musical chords, 2 or more notes that are played at the same time, which produce dissonance, are sometimes called crunchy chords by musicians, and those are my favorite. I love it when I get to sing crunchy chords, or when the accompaniment to my music is crunchy chords. So, interference occurs when 2 or more sound waves interact. In concert halls, interference is undesirable, so engineers designed these spaces with acoustics in mind. Destructive interference can be used in headphones, however, to intentionally cancel ambient noise. Waves that are close in frequency can interfere constructively and destructively at regular intervals. The constructive intervals produce a louder sound, and these repeated louder sounds are called beats. Now, not the same beats necessarily as in like beats within a measure if you're talking about tempo or time signatures in music. It's kind of a different beat in mind here. I will comment one thing about these noise canceling headphones. If you've ever worn them, they are detecting the frequency of different sounds that are coming into them, flipping the frequency, and then playing that flipped frequency into your ears so that it cancels the sound from outside. If you are prone to motion sickness, however, like yours truly, they can make you feel really bad. And I didn't know this till I tried a pair on once in, where was I? Fry's? Fry's. took 30 seconds and I was sick for like an hour. It was crazy. So if you're prone to motion sickness, be very careful if you're going to put these on. How you hear sounds. The outer ear funnels sound waves, the middle ear transmits waves inward, and the inner ear converts sound waves into a form that your brain can understand. This is how the ear and hearing works. The tube that leads from the externally visible portion of your ear, which we call the pinna, and the middle ear inside your skull is called the ear canal. The ear canal dead ends at the eardrum. As sound waves impact the eardrum, it begins to vibrate. On the other side of the eardrum is the middle ear. The middle ear contains the three smallest bones in the human body, the hammer, the anvil, and the stirrup. These bones are connected in such a way as to carry the vibrations from the eardrum to the inner ear. The cochlea is located here, and it contains thousands of tiny hair-like structures which pick up these vibrations, convert them into electrical impulses, and send them to the brain via the auditory nerve. Many people suffer from hearing loss as a result of injury, infection, or age. The application of sound. Sonar is a system of detecting reflected sound waves. We talked about this a little bit before. Sound waves are sent towards a target, perhaps the ocean floor or an enemy submarine, and are bounced back, whereupon they are interpreted to identify the distance to the target. The sonar device measures the time it takes to detect the reflected sound waves. Echolocation, as we talked about before, is the use of sound waves to determine distance. This technique can both employ ultrasonic and infrasonic pitches. Bats use ultrasonic echolocation to see in the dark. Now, if infrasound is below what you can hear, then ultrasound is above the pitches you can hear as a human. Bats use echolocation to navigate and find food. Doctors use ultrasound to look inside the human body and diagnose and treat medical conditions. An image created in this way is called a sonogram. Ultrasound can be used in devices for cleaning jewelry, medical or dental tools, and in autofocus technology of modern cameras. So the ultrasound you're probably most familiar with are these fetal ultrasounds that are done during pregnancy. You've probably seen 100 of them in your life, but we can also use ultrasound for all sorts of conditions that we're trying to diagnose if we want to get an idea of what things look like inside. So let's talk about music for a few minutes. So first I wanted to show you guys this. This is a little more blown up version of what you had in your notes when it came to frequency and pitches. And I want you to particularly focus right in here in your fourth octave, which is what we'll be looking at in just a moment. So we have right here the frequency of each of these pitches. So this is middle C, or C4 in the fourth octave, and you can see the frequency of middle C when it's tuned exactly as 261.64 hertz. This note right here, which would be a C sharp if you're going up the scale, a D flat if you're going down the scale, is 277.18 hertz. And then obviously we keep moving up. D natural would be 293.66 hertz, and so on. Okay. How does this work? Well, if you look right here, this shows you intervals basically, and you can kind of tell how these line up. When your waves line up in a pleasing way like this, and there's like evenly divided, you get a nice harmonic sound. When the division is not even or equal, you get some dissonant sound, which we consider unpleasing in our culture. I also want you to notice something else. A right here, C is highlighted because this is middle C. A is highlighted because it's A440, and this is where orchestras tune. Exactly an octave below is 220. Exactly an octave above is 880. That's nice because there's no decimals there, and you can tell that those numbers are all exactly. You got doubled here, you got doubled here, and then when you move up, same thing is happening. Same thing for all these others. The math's a little more difficult because they're not nice round numbers like 440, but it's exactly what you've got going on here, 130.81 to 261.63. So we're basically doubling as we go up in each octave, okay? And then between the notes within an octave being C to C, D to D, E to E. The notes in between move up by definitely smaller intervals than being doubled. And I wanted to show you here, this would be a C major scale if you just played the white keys. It's a chromatic scale if you play the keys including the black notes or the half steps. There is actually a half step between E and F, which is why there is no black note here, and there is a half step, musically speaking, between B and C, B natural and C natural, which is why there is no black here. So if you're walking up a major scale and you're using only the white keys, you're naturally in a scale going to have a half step here and a half step here. I also want you to notice that your black notes have two names. That's because if you're going up, you read it as C, C sharp D, D sharp E, F, F sharp G, G sharp A sharp B, C. But if you're going down, it is C, B, B flat A flat G, G flat F, E, E flat D, D flat C. Okay, now we're going to listen to some pitches. C major, no sharps, no flats, all natural pitches. C4 or middle C. Go up one step, interval is now a second C, D. Together. A third C, E. Together. A fourth C, F. Together. A fifth C, G. Together. A sixth C, A. Together. A seventh C, B. Together. And a full octave C4 to C5. Together. C major scale with no sharps or flats. Chromatic scale with sharps and flats. C major scale with no sharps or flats. Chromatic scale with sharps and flats. You already heard that. So here it is again, slightly smaller than what we looked at before, and right here, this is the math, if you needed to do the math. So I'm wondering if any of you play instruments. Obviously, raising your hand won't do you any good when you're sitting at home. So here are our different families of instruments. Have a look, see if you see one that you play, or maybe one that you recognize. I know my instrument very well, but I've only ever seen it one time. And that was when I went here, when I needed the instrument recalibrated. That's my instrument. Not a very attractive picture, but those are my vocal cords. And when I needed my vocal cords recalibrated, like any other instrument, whether it be a scientific or musical instrument, this is where I went for help. If you look very closely, you'll see this little white spot right there. That's on my right cord, because this image is taken from above looking down my throat. And That is a lesion or a little scar tissue that I earned after having a really, really terrible bout with viral laryngitis, which is an inflammation of your vocal cords. And when I went there, the otolaryngologist asked me what problems I was having, and I told her I was having issues with my passaggio, which we'll discuss in just a minute. And she asked if there was a particular pitch that I could point to. And I said, well, my passaggio usually sits right around A natural, so I'm definitely having some issues there. So she had me, she pointed this little camera down my throat like that. That's a still image from the video there. And she had me sing sirens just kind of like, ooh, ooh, up and down, up and down. And there was an oscilloscope that was also reading the frequency of the sound I was producing, and those images were showing up on a screen. And it should make like a nice arc up and down on a graph, but there was a little bump in it. And when she zoomed in, that bump was at 442 hertz, and A natural is at 440 hertz. So when you know your instrument well, you know your instrument well. So this is weird but cool. You're going to go watch video number 4, which is a close-up of vocal cords while singing, which is what I saw on screen when the otolaryngologist had me in there. It was pretty fascinating. Okay, we're going to watch a couple of videos here on the physics of music, musicality in particular, and we're discussing vocal music in particular here. But there's going to be some terminology used, and I wanted to give you an idea of what's going on so you're not completely in the dark. So intervals are what I played for you a little bit ago on the keyboard. That's a number of steps between notes. So like if you remember, I said C to D is a second, C to E is a third. In one of these videos, a fifth will be discussed, and a fifth, for example, is like C to G. Vocal pitch is the pitch produced by tightening and loosening of a singer's vocal cords. Passaggio. Okay, this is what I was having issue with when I went to the doctor. It's also known as break tone. The pitch above which a singer can only sing higher pitches using head voice. Okay, so we're going to discuss resonance in just a moment here. So if your passaggio is a little collection of notes right in your mid-range for a singer, and above those notes you can only resonate sound in your head. Below those notes you can resonate sound in your chest or frontal or pseudo resonance. And those particular notes that are in your passaggio you can do in all of those ranges. So you can do them in chest, pseudo, frontal, and head, but often what you use is called mixture, which we'll talk about in just a second here. So, vocal resonance, singers use different parts of their anatomy to best resonate different pitches. Chest voice is where your pitch is resonated predominantly in a singer's chest. For lower notes, it's not really a thing for higher notes, and you can think of the sound as dark. If you've ever heard like a male opera singer, like a bass with a deep voice, this is kind of a great example of chest voice. Pseudo resonance is where your pitch is resonated primarily in your frontal resonance, but with a little touch of chest. And it's often used to add character to mid-range and lower notes, and you can think of it as kind of a thick sound. Your frontal voice is where your pitch is resonated in between your head and your chest, and you can think of it as right in a singer's mouth. It's mostly for low to mid-range pitches, and you can think of it as bright. Often you'll hear voice instructors use the visualization of send the sound right to the back of your top teeth. You may hear somebody say that if you do chorus or, solo work. Now here's where mixture comes in. This is a blend of frontal and head. It's often used to cover those passaggio notes, which are the notes that sit on your break tone, and it's probably the most challenging resonance to master. It can be very difficult for people. And you can think of it as a spread sound, and it's the kind of thing where you really have to think about where you are aiming your note, where your placement, singers will refer to it as placement. Where am I placing that note? Where am I resonating it? And lastly is head, and this is the pitch that is resonated predominantly in the singer's head or sinuses, and it can be used for low notes, but it is required for high notes above the passaggio, and you can think of it as a very light sound. This is typically most often what you'll hear in choral singing. Now, there's also something called a belt voice, and you've probably heard of this, and this is when a singer uses his or her frontal resonance on notes leading to or within the passaggio. And what happens here is it's largely produced by bouncing the sound off the hard palate in the singer's mouth, but because those notes are the highest frequency notes, that a singer can produce using frontal, they tend to come out really loud. And so if you've mastered a belt voice, then that's what you get. And this is typical of like Broadway singers. Back phrasing. Back phrasing will be discussed in one of these videos. This is when a singer or an instrumentalist will place a note slightly behind the beat, and this is for artistic effect. Triplets. Triplets are when 3 notes are played or sung within a span of 2 beats. So the way you do a triplet, if you're trying to hear it, is you would clap a steady beat and say cup of tea. So if my beat is 1, 2, 3, 4, but I want to fit 3 notes in between the claps, it becomes 1, 2, 3, 4, cup of tea. So cup of tea, all 3 of those words came within 2 beats. So there are some triplets in one of these examples we're going to be hearing. Vibrato, this is when a musician or vocalist intentionally causes a minor repetitive fluctuation in pitch. Violinists will do this by wiggling a finger on a string. The opposite of vibrato is straight tone, in which there is no fluctuation in pitch. Modulation is a change in key signature. So key signature is denoted by the placement of sharps and flats within a given scale. We were doing C major earlier when I was showing you pitches. It gets a bit complicated, but in general, there are 15 major and 15 minor key signatures in Western music. I should say key signatures, but you'll live. So there will be modulation discussed in one of these videos. So now I want you to watch video number 5. Video number 5 features Seth Rudetsky, and he is deconstructing the song He Plays the Violin from the musical 1776. Seth Rudetsky is a character. He is one of the DJs on Sirius XM Broadway channel. He is very well known within the New York music theater scene. He is a composer and a conductor, obviously a DJ. He kind of knows everybody there is to know, and he's entertaining. But note that this song is being performed by Betty Buckley, and the he that she is discussing in the musical 1776 is Thomas Jefferson, who was a violinist. She is Thomas Jefferson's wife in this musical. So go ahead and watch Seth. And next, we're going to watch a video here on this gentleman's opinion of how autotune destroyed modern music. So now that you've just seen Seth Rudetsky give a serious breakdown of the musicality of a vocal production of a particular number, a particular song, that he broke it down into tiny, tiny bits and talked about all the artistic stuff that was put in with all of the physics to make it music and not just sound. Now watch this bit on autotune. And lastly here, what does music have to do with science? Well, science is deeply ingrained in many aspects of the arts, especially music. This becomes clear when looking at music through the lens of STEM education. Music connects language, math, time, history, religion and faith, and multiple branches of science, physics, chemistry, and biology. Certain parts of your brain perform certain tasks and retain certain information, and music has the ability to connect those areas. So this graphic image here on the left, this is a musician, and this is the musician's brain listening to music on the left, and on the right, that is the musician playing his or her instrument. You can see how lit up that brain is. Now, regions of the brain do particular tasks, and when you're playing an instrument or singing and reading music, your whole brain will light up like that, and that is because it connects various areas of your brain. And there are very few other things that do that. So I want you to watch video number 7 on how using music can help unlock Alzheimer's patients' memories. And lastly, I want you to, if you can in your life, learn music. It's for your own good. After seeing that Alzheimer's patient, I hope you realize why. Have a great week. Lab is excused. I will see you back next week.